In this video, we explain sp hybridization by trying to explain the bonding in the acetylene molecule. Acetylene is this molecule. This is the Lewis dot structure of acetylene. And when we use VSEPR theory to predict the shape around the carbon atoms, we see that there's two groups of electrons around each carbon atom, and that results in a linear electron group arrangement. Because all of the groups of electrons are bonds, then this molecule is linear around the carbon atoms. And again, our goal here is now to try to look at the orbitals of the carbon atoms and see how we can reconcile what we know about this molecule, and that is the fact that it's linear and it has this sort of bonding structure. Much as before, notice that the natural atomic orbitals fail to completely describe this because we expect to find two bonds, okay? But they should be 90 degrees away from each other. Right? That is the 2px orbital, that might be the 2py orbital, and those are 90 degrees from each other. And it would be impossible to again get to a structure which is linear, where the bonds between the orbitals are, but the angle between the bonds is about 180 degrees. Right? And so what we do is we invoke here something that is called sp hybridization. Right? As with any other hybridization, you can always go to a natural orbital diagram in energy and then go through the steps of promotion and hybridization. Right? That is the 2s, these are the 2p's, you promote that electron here, and then the idea is that in sp hybridization what you do is you are going to mix the 2s orbital with only one of the 2p's, and that means there will be two 2p's left unhybridized, and then the mixing of these two 2s orbital and then 2p orbital is going to give you two new hybrid orbitals. Okay, so that is what we call sp hybridization. And you will have an orbital diagram that looks like this. That is your sp hybrid orbitals, one electron in each, and then you will have your unhybrid. We're going to choose these to be the 2px and 2py orbitals with one electron each. Okay. Now, importantly, when you do the mixing of the wave functions for the s and the p, what actually happens is that these sp, these two orbitals, sp, they're actually pointing in opposite directions, right? So they're anti-parallel, right? So the way that we can draw that structure then is this will be the carbon atom, and one of the sps points this way, that is the sp with one electron, and the other sp points that way, this direction, right? Those are the two sp hybrid orbitals, and now we're kind of ready to try to use this orbital picture to explain the bonding in acetylene. Right, so we have to complete the orbital description of that carbon atom. Notice that we still have to draw there the 2px and 2py. We're going to choose the x direction to be up and down, and then the 2py direction, or the py direction, will be coming in and out of the plane, which is a little difficult to draw into the dimensions, so we're actually going to draw it at an angle here. So that would be your 2py with one electron. Okay, now we'll look at this other carbon atom, and the orbital structure will be exactly the same. Right, so you will have here an sp hybrid orbital, and then pointing the other way, you will have the other sp hybrid orbital, and then you would still have here a 2px, which is singly occupied, and then a 2py, which is also singly occupied. Come. Alright, so we already know right away that that is a sigma overlap between two hybrid sp orbitals in those carbon atoms. Okay, and then we can explain the bonding with the hydrogen atoms as an overlap between the 1s wave function of hydrogen and the singly occupied sp wave function of carbon. Same thing on the other side, 1s orbital, these are all sigma bonds. And then we quickly notice that there's more possibilities for bonding between these two carbon atoms. Now, you have your two px orbitals that are pointing up and down, and that means that you can have a side-on overlap, right? So that is what we call a pi bond, right here. And then the two py's are coming in and out of the plane, right, this way, so there can also be a side-on overlap on this other axis, so there will be another pi bond. Okay, very clearly we can see that we can go beyond the Lewis dot structure in the SAPR theory by saying that this triple bond that you have between the carbon atoms is caused by a sigma overlap between hybrid sp wave functions in those carbon atoms, and then pi overlaps between unhybrid 2px, 2py orbitals in those carbon atoms. Okay? And we know that the structure here should be linear 180 degrees, because when we build these hybrid orbitals, okay, and the SPs are actually pointing in opposite directions, and they do form a 180-degree angle. Right, so in this video we have explained the structure and the bonding of the molecule acetylene by invoking sp hybridization.